In this video, we're going to go back and review arithmetic sequences and geometric sequences. So I've pulled up the old worksheet that I did a long time ago, and probably like the first 9 weeks. And back then I showed you two types of sequences: arithmetic sequences and recursive sequences. But really, those arithmetic sequences are just part of the recursive ones. The only difference was that recursive formulas are written so that the previous answer is used to find the next answer. But arithmetic sequences just need the common difference, and then you add things back on. The formula for an arithmetic sequence is this right here. The new term will be equal to the first term plus n minus 1 times the common difference. And for a recursive formula, the next term is equal to whatever came right before it plus the common difference. So the difference between these two is the arithmetic one, the general arithmetic one, starts with the very first term. And then whatever term you're on now, let's say this example down here, if you were on the 24th term, then you would do the first number, 3, plus, it says n minus 1, so that would be 24 minus 1 to get 23, and then you multiply that by the common difference. And that'll give you an answer of 824 equals 118. But with recursive formulas, you're not allowed to skip any steps. If you wanted to find the 7th term, like we did down here at the bottom, then we needed to find the 6th one. And in order to find the 6th one, we have to find the 5th one. If we want to know the 5th one, then we have to know the 4th one. There's no skipping because each one is written so that it depends on the last one. So what I'm going to do is I'm just going to erase what I have here. And I'll hope that you'll be pleasantly surprised by how easy this is now that we've learned so much since back then. From one term to the next one, from 12 to 16, that's a plus 4. From 16 to 20, that's also a plus 4. And the pattern continues, plus 4. Since we're adding 4 each time, the common difference is 4. That number 4 is happening over and over again, but it's just being a plus 4. Because it's only a plus 4, that means we need to multiply it by something else to make it happen repeatedly. What else we have to multiply by is n minus 1. n minus 1 times 4 will add the number 4 repeatedly a certain number of times. The only thing we need to make this into the correct formula is we need to write the starting number. The starting number is 12. So we're just going to put 12 plus n minus 1 times 4 equals. Now let's just check it. A1 will be equal to 12 plus 1 minus 1 times 4, and that makes 12 plus 0, which is 12. And that does match our first answer, so that's right. In number 2, we start with the number 5, and then we go to the number 1. That would be a minus 4, but from the number 1 to 1/5 is minus 4/5. From the next one, it'll be minus, I don't even know what, like 4/25. So that's complicated, and it really shouldn't be. So the next way we're going to do this is we're going to do it, and we're going to look for a different type of sequence. We're going to look for how is this changing through multiplication. From the 5 to the 1 is a times 1/5. From 1 to 1/5 is a times 1/5. From 1/5 to 1/25 is a times 1/5 again. So we're having this number 1/5 that happens over and over and over. And if you didn't understand how I just got that number out of nowhere, what I did is I took the next one and I divided it by the previous one. which is exactly what you just did yesterday whenever we were learning about exponential functions. If we take the number 1, which is the second term, and if we divide by 5, which is the first term, well, that's just 1/5. So now that we know that it's changing by a factor of 1/5 over and over and over, that means that 1/5 is happening over and over through multiplication, which means it gets an exponent. The next thing we need is the starting number. The starting number is 5. 5 times 1/5 to the power of x will be equal to an. That's our equation for the sequence. And this is the geometric sequence. Whenever you have a formula that looks like that, that's a geometric sequence. Let's look over here. This one has fractions, so you might think that it's geometric. But if we look, 5 halves is the same thing as 2.5. 3 halves is the same thing as 1.5. So from here to here is a minus 0.5. From 2 to 1.5 is a minus 0.5. From 1.5 to a 1 is a minus 0.5. So all we're doing is we're subtracting 0.5 over and over and over. And because it has a negative sign, I'm going to put that in parentheses. But since that's happening repeatedly, that's subtraction. That means that this is going to be an arithmetic sequence. And we're going to have to multiply that in minus 1 times. And then we just write the starting number. 5 halves plus n minus 1 times negative 0.5 will be equal to an. And if you want to, we can check it. A2 will be equal to 2 minus 1 times negative 0.5. And we're going to start with 5 halves plus that. 2 minus 1 would be 1. 5 halves minus a half. 5 halves minus 1 half is going to be 4 halves, which is 2. And that's what the answer for the second spot is anyway. So that means that's the right formula. Let's check out this one, number 4. From negative 3 to negative 12, that's a minus 9. From negative 12 to a negative 48, I don't want to do that. It's like a negative 36. No, thank you. Let's try it a different way. Negative 3 to negative 12, that's a times 4. Negative 12 to negative 48 is a times 4. Negative 48 to negative 192 is also a times 4. So we're having this common ratio. 4 is the answer to the common ratio, and the ratio came from negative 12 divided by negative 3 to get 4. This is the common ratio. Now let's write the equation for this. an equals, we're going to have this 4, and it's happening repeatedly, which means it gets the exponent. Oh, I guess I can fix it in the last one. Since we're using n's for sequences, this would be 4 to the nth power. And over here, this would be 5 1/5 to the nth power also. And all we need in front of this is the starting value. Negative 3 times 4 to the power of n. But let's check this. Let's make sure that this is actually working, because I feel like I might be forgetting something. Let's try a1. a1 would be negative 3 times 4 to the 1 power. 4 to the 1 power is 4. So that's negative 3 times 4, which makes negative 12. But negative 12 is actually the second term, not the first one. We want it to show negative 3 for our first answer. So we need the sequence to scoot back one step, because right now it's giving me negative 12 when it should be giving me negative 3. So how we can make that slight modification to go back one step is we use an n minus 1. Now let's try this modified formula. Negative 3 times 4 to the n minus 1, and in this example, n is 1, 1 minus 1 power. That's negative 3 times 4 to the 0 power, which is negative 3 times 1, which is just negative 3. And that's what we wanted, and now it's working. Let's try a second example, A2. Negative 3 times 4 to the 2 minus 1 power equals negative 3 times 4 to the first, which makes negative 12. Okay, it's working. Let's change this one. This should also be an n minus 1. I would have known that if I just checked it the first time, but now let's try it like this. Let's try A3. A3 equals 5 times 1/5 to the 3 minus 1 power. That's 5 times 1/5 squared. That would be 5 times 1/25. 5 times 1/25 is going to reduce to make 1/5. And that's what we wanted for the third term anyway. So this is the formula that's going to work. It looks like there's something in common between geometric sequences and arithmetic sequences, and that's that arithmetic ones multiply by n minus 1, but geometric have an exponent of n minus 1 in their answer. Let me do one more geometric with you just to make sure that this is working, and it's always going to have that n minus 1. So from 3.25 to 9.75, that's a times 3. Here, that's also a times 3. So I'm going to have a 3, and it's going to be raised to an exponent of n minus 1 times. And we're going to multiply that by the first term in the sequence, 3.25. 3.25 times 3 to the n minus 1 power should be equal to my an. Now let's just check that. I'll do it with the number 2. A2 equals 3.25 times 3 to the 2 minus 1 power is 3.25 times 3 to the first power, which is just 3.25 times 3, which is 9.75. And that's what we wanted. Okay, hopefully this is enough examples of geometric and arithmetic.